continue the meeting. Yesterday, that was the last transparency. I was speaking about basics of FX and equity derivatives pricing, and we arrived to the Dupire formula, which I think I presented more or less complete way as the only thing. So I remind you my principle. I will give you some proofs of theorems. If they are not longer than 2 slides, if they are longer, so it's not possible, I need a blackboard. Maybe there are some people who are able to give some reasoning on using slides. I can't. So the Dupire formula. So what is a Dupire formula? A formula which links market observables, namely the option prices, with market parameters. So parameters, especially the most important model parameters, the most important one, the volatility. So in most cases, okay, not in most cases, but in the simplest cases, volatility is just the parameter. So it's the most important one. And that may be applied 2 ways. So the most popular one is from market observables to model parameters. But we may revert that argument. So it's a general formula. And then, how to price please move that window away. Okay. How to price? Because sorry, I'm distracted because something appears on my screen permanently. You probably don't see that, but
don't worry, Dariusz. It's always in the.
Yeah, I know it's always in something, but. That
yes, don't worry.
I can't see my presentation.
Yes, but it's always on the title, so don't worry.
But do you see that? Please leave this window.
It appears and disappears. It appears. No, I can see it, but no, it's going to disappear.
So you see it as well. So
yes, but it is always in the.
Adrian, how to remove it?
I don't know what is it. I think it is from your computer, but now it disappears.
I have no idea. Now it's disappeared. Yeah.
Yeah. So I click. So I should either leave with that or try to fix it. Okay, let's try to leave that. No, but it's. I don't know what I'm talking about because of that. That's the pleasure of internet lectures. Once again. Okay, let's. Why is that also slow? So there are always technical problems with. Okay, so now let me open way. So stop and restart. Okay. So the next next part of the lecture is how to price. Now, Markovian projections was already there. Local stochastic volatility. How to price derivatives, and of course they are namely options. There are hundreds of numerical methods, but some of them are more tricky, some less. But what's the general scheme of pricing options? So that's using the Markovian potential theory. So it's created some 50, 60 years back by several people. So what is that? That is linking stochastic processes, Markovian stochastic processes, with partial differential equations. And with partial differential equations, we've got at least 200 years of experience, so we know some tricks how to solve them. So to a Markovian process, to a diffusion, namely of that form, we link an operator, which is second order derivative differentiation operator. So with terms of zero order, which represent for discounting, of first order, which represent drift, and second order, which represent diffusion. And we've got such a, since the process X is Markovian, we've got such a representation that there exists a function which is discounted, expected discounted option price. So this is, U is just an option price. Of course, we may put here any other function, any other type. And since this is an expected value of a random variable, this is a martingale. Yes, so since U is a martingale and we may use eta formula, so the eta formula is of that form, the dw term is of less importance, and then just take an expectation of that term. Yes, so after taking an expectation, we get a partial differential equation of linear type. So a very standard notion for which we've got hundreds of methods. And if you, so what is X? So X is the process of minimal dimension that is Markovian. So in the particular case for Heston model, it will be two-dimensional. So the underlying and stochastic volatility, yes? So this process, this two-dimensional process is just a Markovian process. There are other stochastic volatility models because we cannot say that one is right and the other is wrong because they serve for various purposes. So the Dupire Bergami stochastic volatility is two-dimensional. So the Markovian process will consist of 3 dimensions. But all that may be put into the linear partial differential equation scheme to price. And my experience is that when we deal with Heston models, so that's better to use very standard, so already present in libraries, tools to solve the Kolmogorov equation, Kolmogorov backward equation, then do all the tricks with the Laplace transform. Because Laplace transform is a tool from a pre-computer era. So that was the way how people did it, not having computers, but numerical methods of complex analysis are not very efficient. Okay, so when we've got that tool, as a bonus, we get pricing of American options. So, as you probably remember, what is an American option? So, an option which may be exercised at any time. So, European option is exercised at maturity, and American option may be exercised anytime up to maturity. So that's, in mathematical terms, this is an optimal stopping time problem. Yes, so I think you may agree with that formula on the screen. And how to derive the pricing formula for American options. So, since the option price is a sub-martingale, it's a sub-martingale because any stopping policy is at the best optimum. So this is, any policy is suboptimal. So this term is a sub-martingale. So using this argument from the slide before, we get this inequality. So taking eta formula, but exactly the same, but here we've got an inequality and not equality. Then we take expected value and get that inequality. But on the other hand, we've got the option price much be less than its intrinsic value. Yes, because when the option price is less than its intrinsic value, we just we don't do anything. We let the underlying proceed. But when we reach the moment when these two values are equal, we just exercise the option, yes? So we've got this inequality. And there is a theory when we take and there is no other possibility. So we must exercise the option or not exercise. So either this equality here in this term holds, or this one. No third possibility. And we've got this equation here with the terminal boundary condition. And that's all. And we need some mathematics to know that these three conditions determine a unique solution. There's a problem with smoothness, but say in applied mathematics, we take the assumption that all functions are differentiable. So, because when a function is not differentiable, it's a Schwartz distribution. So that's not a problem. And we've got a nice picture here that the whole state space may be divided into two parts. The stopping area, where we exercise the option, or continuation area, where we don't exercise it. No third possibility. So where is ice here? Do you have an idea? Question to the audience. My first question to the audience. So somebody try to answer. It's a very, very nice picture for today. Ice. Where is ice here? Elisa, is there anyone trying to answer? No, nothing in the chat. Zoom, meeting control, Zoom. No, nothing in the chat. Okay, so let me answer the. It's exactly those that kind of equations was discovered on the occasion of investigation the melting ice. Because imagine the very general situation. We've got a phenomenon. So it's not physical, but economic, but irrelevant. This is something is happening. And the equilibrium for that problem is that either we take one decision, we exercise their option, or not. So we've got two mechanisms to run one phenomenon. exactly in the case of melting ice, because there is some thermodynamics of the liquid water, some thermodynamics of the ice, and physics, which rules, which creates a free boundary between them. So the energy propagates differently in water than in ice, but still this is one phenomenon. And here, what we see here is so-called free boundary. Free boundary between melting ice and water. I need one answer from the chat. So does anyone has a comment on this phenomenon? Do you like the look of the free boundary? One word, how it is. Maybe I should ask questions to concrete people, to Anna Merkel. Yes, what's your opinion? Nobody. Okay. So the word is irregular, because the free boundary between stopping area and continuation area is just created by the mechanism, and that makes the problem tough to deal with. So free boundary problems from numerical points of view are very difficult. So there are several methods how to deal with that, how to discriminate between the stopping area and the continuation area. And I think the most popular one in finance is the so-called Longstaff-Schwartz method. So this is nonlinear regression method. So let us discretize the time period, so the maturity. So in applied mathematics, we don't distinguish that much between the continuous time problems and discrete time. So sometimes it's quite popular that we make all the argument with continuous time, but when we pass to solving practical problems, we take discrete times and we don't bother with convergence and so on. So let us discretize the problem. this discretization may be very tight if we would like to have the illusion of continuous time. And let us define by U the propagation of the V is the value of American option. And this value propagated one step further. And by the Markov property, of course, the value of the American options is maximum of the intrinsic value of the option, the payoff of the option, or value of the propagated value. Yes, because either we exercise the option or not. No other possibility. And then, knowing from the Hilbert space, so this is L square theory of random variables, we know that the propagated value, the U, is minimum over all functions which are functions of the current state of the Markov process. Yes, so, okay, so it's a minimization problem. Perfect. Of course, we can't minimize on the set of all functions, but we may restrict this class to a reasonable one. So what reasonable is? It is, of course, not a mathematical notion, but from practical point of view, we find polynomials, trigonometric series splines. And how it works in practice, that we generate a number of Monte Carlo paths of the random variable, and just use nonlinear regression for a class of functions. For this class. And the function which minimizes this term, so this is square distance from the optimal value. This function h will be the propagated value. And then we take the minimum with the payoff. And that works, I would say, in even large dimensions. But since this method is mostly heuristic, so it's not much stable, and we must use some tricks to improve it. And so that is something you should know working as a quant for a bank. And as far as I know, this method, called also American Monte Carlo, was not invented before. So that was created for the purpose of mathematical finance. So that's the contribution of our community to the general numerical methods. So it is applied elsewhere as well, but comes from mathematical finance. So this is the most efficient method of solving optimal stopping problems in larger dimensions. And we may use also another trick. So, and again,
Dariusz, we have a question in the chat, sorry.
Yes. Ask questions. I was very close to stopping the lecture because nobody is there in the room.
You know that here in Europe, we are not used to interrupt the speaker. But
yeah, in the room it's all right because I can communicate with eyes, yes. But here's only my computer. I know my computer. He knows everything what I have to tell about. So
there's a question that says, what's the bias in Longstaff-Schwartz?
What's
it's about the bias? The one we make that, I don't know the name because it's
so Longstaff-Schwartz method consists only of biases. So it's completely unstable because, you know, everything depends on the class of functions we choose. And every class of function is wrong, but for that particular problems, it may be not that wrong. But this is desperation in practice. Longstaff-Schwartz method is, as far as I know, the only one which gives some reasonable results in larger dimensions. Because when we want to discretize and do it some numerical methods, it takes eternity. So it's desperation, but conceptually it's quite clever. So if you want to use Longstaff-Schwartz method, first ask a more experienced friend what class of functions would he or she choose. That's the first step. And there is one more trick. On optimal stopping, because what is we must take, we must remember the whole situation. So it's not, we are not solving an autonomous problem, but it's a part of bigger problem, which is pricing of American options. So in order to price, we must first calibrate. And when we calibrate, there is always a question to which set of options. So conceptually, pricing of American options is choosing the best European You've got a family of American options with of European options with a number of maturities, and we have to take the best one of that, yes? So we should calibrate the model to exactly this one set of options. So the problem is essentially Markovian in dimension one. So this is the way how a trader thinks. It's Markovian in dimension one. So why should we pay so much for solving such a difficult multidimensional problems, optimization problem? Let us reduce the problem to single dimension. So what are methods of that reduction? So first one is just take Longstaff-Schwartz in dimension one. So we know that the process is not Markovian, but we don't care about it. We generate M-independent Monte Carlo paths, then find the function that minimizes that term, and we are happy. Yes, and this is the way how people use Longstaff-Schwartz. So just breaking the dimension collapsing the dimension to one. We may do it a bit more formal way. So use Markovian projection. Yep, so you remember, yeah, Markovian projections, which is a byproduct of Dupire approach. So we take this one-dimensional stochastic process, for which the option pricing, European option prices coincide with the ones that we have from the market or from another model. And for that problem, we write down the variational inequality here and just solve it. And in solving variational inequalities in dimension one is relatively easy. We don't have to do it by Longstaff-Schwartz, but Longstaff-Schwartz is quite efficient. By the way, Schwartz or Schwartz, he's Chilean. So in Spanish, you say Schwartz or Schwartz?
We try Schwartz.
Schwartz. Okay, so wrong. We use Longstaff-Schwartz and or say trees or finite differences implicit or explicit. So, but the optimal stopping in dimension 1 is relatively easy to solve. And when we compare that, say, this naive Longstaff-Schwartz I recently did it, in dimension 1, with some other method after collapsing the dimension of the processed one, they practically coincide. So differences between prices are in basis points. They practically don't exist. So that's that is everything that I wanted to tell you on equities. So maybe some questions if you have any. And then after a short break, we will pass to interest rates. So for interest rates, I will need at least 4 hours of lecture, maybe 5. Then 2 or 3 hours credit risk. And the last hour, I will tell you about life in banks, hedge funds, and so on. So how a mathematician might survive without tight knots. So nobody wears ties this way. Tie knots, of course, got a very interesting theory. So it's nice algebra, but we'll skip ties. So
I have a naive question, Dariusz. So in the financial industry,
yes,
American options are evaluated using partial differential equations or using binomial trees, or
this 90%. When we in smaller dimensions, we try to use finite differences. So small dimensions up to 3.
okay.
They've got better computers, so this is up to 4. Larger dimensions, American Monte Carlo, 100%, and in dimension 1 to 3, Longstaff-Schwartz is also practical.
Okay, okay, thanks. I don't know if there are more questions. So if not, we can stop here and we meet us again at 10 o'clock.
At 10 o'clock, maybe, but punctually 10 o'clock.
Yeah, yes, super. Start recording again.
Adrian is not there. She's
yeah, it's now working.
Oh, okay, you're here.
Yeah, you can start.
Okay, so so hello everybody again. So we are moving to another subject. So from my point of view, probably more important. So the purpose of the talk is to condensate all necessary knowledge necessary in my private view on interest rate modeling from the, not from the economic point of view, but mostly for interest rate derivatives. Okay, so the plan of the talk is I will tell you some words about the market, then we'll introduce the concept of forward measure. By the way, change of numeral rings a bell or not? I need some people to answer yes or no. So 3 letters at most. Type. Change of numeral.
I think that many students don't know what is a change of numeral, perhaps.
Okay, so let's start. We'll start from the beginning. So the celebrated Heath-Jarrow-Morton model, then short rate model. So normal lecture is that we start with short rate models, and then move to Heath-Jarrow-Morton. But I've changed the order, you will see why. Then BGM model, Chayet model, or Chayet, I don't know. So I don't know Aaron personally, so how to pronounce his name. And then the pure formula for interest rates. When someone wants to hear something about something else, it's time to write it down in the chat area. So, okay, the market. What are interest rate products? So first, the simplest ones are fixed and float coupon bonds. I don't know how it looks in Spain. Do floaters still exist in Spain, or you don't know? They are retail bonds normally. Okay, irrelevant. Fixed coupon bonds are, say, the dominant part of interest rate products. Forward rate agreements. So they are, say, simple but very liquid products dealing with forward rates. Interest rate swaps. So that's a huge, massive market. So when we compare numbers and global product of the world and exposure of in interest rate swaps, so interest rate swap will be, say, 10 times more than GPD, global product of the world. FRA's options, so called caps and floors, so options on future interest rate, put or call options, swap options, massive market, billions, exotic interest rate options, exotic coupon swaps. So you may not remember what was some eternity ago, say 13 years back, before the crisis, so there was a massive variety of exotic interest rate products. These
Dariusz,
days,
I'm sorry,
yes.
I will interrupt you because we have another question.
Yeah.
How does the market for interest rate futures compare to forward rate agreements?
Okay, I don't remember exact numbers, but both are massive. Massive numbers. So really, no, billions wouldn't be massive, trillions. Trillions of exposure.
Okay, thank you.
So I don't know. I think the public market is going to be bigger these days, but I'm not certain. And everything So it's based on not traded bonds, so called zero coupon bonds. What is a zero coupon bond? That if you are a holder of that bond and I'm an issuer, I promise you to pay you €1, say, in 10 years time or 1 year time. So short-term bonds exist up to 1 year and they are called bills, treasury bills. Then I didn't see in the market, but you know, everything is possible. So that's the how the interest rate market looks like. A loan may be considered a bond as well from at least economic point of view. And about that question, how the exposure in the interest rate derivatives looks like comparing to other asset classes, so namely equities and FX. So on the left-hand side, we've got exchange-traded options. On the right-hand side, over-the-counter options. So between counterparties, interest rates are blue. Other products are gray and orange. So you see that in the public market, equity options are traded. So in existing, so noticeable volumes. For OTC market, equity options are not that traded, but FX products are liquid. And that is true. Maybe numbers have changed for the last, how many years? 7 years, but the proportion is similar. And my first question during this this lecture, where did I lie here? There is a lie in my statement. Did anyone notice? You need some extra knowledge. Did anyone notice a lie? Guess. Okay. So I lied. These numbers are in terms of notional. So in terms of market value, of course, the proportion will be different because we've got very low interest rates these days. So that will be not 90% interest rates, but say 60% interest rates, but above half. So it's still the most important asset class. And why people don't, so this time's interest rate research is practically frozen. I don't know why, but okay, if you are interested in industry career, something you will have to learn. And that's the most liquid product, the way how interest rate swaps are quoted. So what an interest rate swap is, all of you know, I guess, but roughly speaking, you exchange fixed coupon for float coupon. What do you trade trading interest rate swaps, and why they are so liquid? Anyone tries to answer the question? What is truly traded when we trade interest rate swaps? Nobody? I give you 1 minute more, because that's an important issue, and we should. Okay, so after this 1 minute has passed, we trade what are floaters. So floaters, bonds with floating coupon, practically don't bear interest rate risk. Their duration is very short. So when we exchange floaters by fixed coupon to fixed coupon bonds, we trade interest rate risk. And that's the upside of interest rate swaps. So without practically much cash flows, bank may exchange interest rate risk. So the bigger banks may take interest rate risk from smaller ones, or mortgage houses and so on. So that's very crucial even these days. Mortgage in Spain is mostly on fixed rate, yes? Come on, I don't believe no one's got mortgage. I guess it's fixed. So practically, behind every mortgage.
We have an answer in the chat. We have an answer in the chat. Equilibrium swap rate between two legs.
Yes. What's the question?
No, I think this is
okay.
An answer.
Huh? Yes, so there is, behind every mortgage, there is a lot of financial engineering. Because interest rate risk exists, and banks don't like it. So, and have to leave it. Okay, so that's the most fundamental pricing, which is, I guess, done by computers. So humans don't bother to deal with such simple formulae. So since this is about interest rates swap pricing, so on one hand, we've got a floater whose duration is equal to 0, so price is always equal to nominal. And on the other hand, price of a fixed coupon bond with the coupon equal R. Yes, so these are payments, discounted payments associated to the fixed coupon. and then at the end, the nominal is paid. So this is the way from zero coupon bond prices. I remind you, zero coupon bond is an offer to pay you €1 at time capital T. You'll get €1 at capital T. So this is one way how to get coupon bond prices knowing zero coupon bond. And this is the practical way how to calculate zero coupon bonds or discount factors knowing the interest rate prices. And of course, we've got that not sophisticated property that offer to pay you €1 just now is worth 1, and it's better to get €1 tomorrow than after tomorrow. So that's, so look at that mathematics, which is for a kind of primary school mathematics, but economists consider that sophisticated. And then let us pass to true mathematics. But okay, from practical point of view, this is important. Okay, one more picture that yield curve means family of zero coupon bond prices normalized, so divided by time, may have such a shape called normal, inverted, flat. These days this is around here, around 0. So, but some people say interest rate will rise. Okay, we'll see. Okay, so now let's introduce mathematics. And B, price of a zero coupon bond. And let us take the discount factor. So 1/R is called savings account. So it depends on the book. So people use various terminology. And as you remember, the fundamental asset prices theory, so absence of arbitrage is equivalent to that discounted prices of assets are martingales. Yes, you've seen that in the case of equities. The difference here is that zero coupons and savings account are somehow linked to each other. Yes, so that's on one hand, it's more complicated, but on the other, it's simpler because we've got only one asset, which is time value of money. There are no equities, there's no credit risk, only that, only zero coupon bond. And we'll see how much mathematics can be done with that. Quite a lot. So that term called M, which is discounted zero coupon price, is a martingale. Positive continuous martingale, because at the beginning of our lecture, we restricted to continuous processes, winner processes. There are no jumps. So theory with jumps is a bit more sophisticated, and my purpose is rather to show you simplicity, but richness as well of the financial mathematics than its complexity. So it may become complex, but first you may have a look from above. What is that all about? It's about martingales practically. So, okay, this is a martingale. So we've got a martingale, Dupire martingale representation theory. So there exists a stochastic process sigma called bond volatility, such that B follows that equation. Yes, so that's we've assumed that the savings account has finite variation to avoid square brackets. So, and M, of course, follows this stochastic equation. But looks simple, but what is complex here? Do you see the complexity, the potential variety of pitfalls? Because T is not just a number. It is a family of maturities. So we are speaking about random movement of not a point, which is something like exchange rate or equity price, but movement of such a quantity which consists of a line. Yes, imagine that. The whole term structure, which consists of many points, moves forward randomly. So we are in the area of stochastic differential equations in infinite dimensional spaces, because the movement takes place in an infinite dimensional space. So it's, from mathematical point of view, it's quite a complex phenomenon. But we've got several keys how to deal with that. Okay, then when we taking into consideration this equation, so this is a linear equation, but still sigma is a stochastic process, we may relatively easily solve it. So, okay, I wouldn't call it a solution, so it's rather another representation of the stochastic differential equation in a larger space. And we've got a nice representation in terms of this martingale of the discount factors. I will speak about a few words about it later. It will be rather about a mathematical issue. And then the general concept, our general task when we price European interest rate derivatives consists of finding expected values of that term. Yes, so Xi is an FT measurable random variable, intrinsic value of the claim, and R is just discounting. And now, let us introduce new probability measure, which is indexed by the letter capital T. So it is called forward measure. So this is from that approach. And this definition is very simple. We just multiply the density is just value of M. Remind you that M is a martingale with such a stochastic differential, so starting from 1. So we are in the Girsanov-Wert. Okay, so since we are in the Girsanov-Wert, we may use all the machinery of Girsanov measure transformation. So it is, of course, a probability measure. And moreover, W with index capital T, so defined. So we add to the initial Wiener process the integral of the volatility. This is a Wiener process under the measure ET. If someone is not happy, ask questions now. Because it's I would say, the crucial part of the methodology. Okay, so everyone follows, so let us proceed further. And then
we have another question that you
yes.
But okay, in a swap striping, isn't there some interpolation needed if you have few quotes?
Yeah. So back to swaps here. Of course, in the swap striping, there is an interpolation needed, and that's a serious problem. What to do? Which interpolation to choose? And the answer, no. So where is the problem? It's not a mathematical problem, because any interpolation is good, because you are in a very simple word from mathematical point of view. But volumes of interest rate swaps are huge. So if we take an interpolation which may cost us, I don't know, half of a basis point, it will be millions. So it's an existing number. And what is the answer? The answer is to take market standard, best from totem. As far as I remember, market standard these days is splines on discount factors. Second order splines on discount factors. That's the way. I did use linear interpolation on discount factors, and it did work. So traders didn't complain. They are using money. So, but you know, there are two ways of losing money in the markets. One is blow up. So when something happens and you lose millions, tens of millions, or bleeding. So use a couple of $1,000, but every day, and it's difficult to spot. So taking the proper swap rate interpolation is a way to avoid bleeding. So as I said before, there is no deep mathematics there, but it is important. So don't neglect that problem while working for a bank. So I understand. So I was like that. I wanted to solve serious mathematical problems and don't bother me with proper interpolation. But it's not good approach in a company which want to make money. Okay, back to our ship. Yeah. So we are here. So under this new measure, this expectation is equal. So just algebra, that term. You know what we have, just algebra, look at the definition of M and definition of the Wiener measure and makes simple transformations. What have I done here? Anyone sees this simple and small formula? What does it say? Question to the audience. Why forward measure is so important? Okay, so the answer will come from me. We have transformed a random discount factor, yes, random and strongly correlated with the underlying assets. So something what may bring a lot of complexities to the problem, to a deterministic short trade. We've reduced a interest rate derivatives pricing to equity derivatives pricing. Under the forward measure, everything is simple and beautiful. Not that simple, but that makes life much easier. Okay. And then we've got a lemma. It's nice playing with martingales. So if let Xi be a stochastic process, and this guy, this term, is a martingale under the measure E, the called spot measure. Then Xi is a martingale after the forward measure. And here you have a sequence of equalities. You may recalculate it at home and test if it is true, but this is traditional martingale playing. So if you had a course on martingales, you made many such exercises. And this is a very important lemma. And an example of that is especially important. So LT is the value of a forward rate. Yes, so a rate which prevails from T minus delta to capital T, and this is our current estimation. So the notion, the word forward appears quite often in the interest rate derivatives pricing theory. So everything is about our thinking of the future, bond prices. So because why a zero coupon bond is worth this value and not another one? Because this is our expectation of the value of money in the future. We are thinking what finance is about, thinking what happens in the future. So if you keep that approach, that way of thinking, you will be much successful even if you don't know mathematics. But of course, mathematics helps in keeping the future in your head. So if L is forward LIBOR rate, so current expectation of the future LIBOR rate, then LT multiplied by M is a martingale. Yes. So taking the lemma into consideration, LT, the forward LIBOR rate, is a martingale under the measure ET. Central property of forward trades. And first, I used first time the magic word LIBOR. Did you hear before about LIBOR and what happens with Mr. LIBOR? Try to answer. This is not a mathematical question, but an attempt to locate your financial knowledge. Dear audience,
we have some answer. We have some answers in the chat.
Yes, yes.
One is LIBOR was discounted, and the other one is manipulation.
Yeah, good. The only answer?
Only two answers.
Huh? Very good answers. These answers hello, David. These answers means that you're interested in what currently happens in the market. This is good. Because when you, with your fresh PhD, send a CV to a bank, they will ask you about math, of course, but they will be interested if you know what you are going to do, the general environment. And LIBOR is very magical word. So LIBOR means London Interbank Offer Rate. So this is a rate that more or less bank lend and borrow money from each other. And I lied to you, of course, using the present tense. Because this is practically past. LIBOR was manipulated. Why was LIBOR manipulated? It's a question to me. LIBOR was manipulated because it became too little liquid. People didn't care too much about LIBOR transactions, so it became a debt rate, easy to manipulate, and these manipulations, of course, some people made money they didn't deserve, so it's always bad. And it has shown us that this is not a good rate for interbank transactions. And LIBOR is going to be switched off at the end of the day and being replaced by, and that's a good question, by what? Because, you know, we are in such a situations that banking didn't stop because LIBOR is not quoted or not correctly quoted. So interbank transactions continue. Bonds and swaps are traded. Loans still exist. Loans are given by banks. So, but the benchmark for such an activity became not very clear. So people are working on switching from LIBOR to something else. And Europe is not clear what will be next, and it's 6 months to go. So They don't work very fast, they're not very responsible, but it's the same with Japan and America. But I will be using the word LIBOR as benchmark rate. Knowing there is no more LIBOR, or there will be no more LIBOR. Okay, so that was a financial comment to mathematics. Back to maths. Okay, so this approach, this forward measure, may be constructed even more complex way. So this forward measure ET was constructed with respect to one payment at maturity. But if we got a family of payments, namely payments at time capital Ti of the size Ki, so imagine there is a line and at every time we get or pay some money. So the simplest situation is when we deal with a bond or a swap, and at times Ti just coupons are paid. And we may define discounting associated to such a family of payments. And of course, pricing of interest rate derivatives of, say, some swap options called swaptions. So Englishmen love such a linguistic place. So consist of pricing some random value, some intrinsic value of an option, some money at defined times in the future. And this forward measure paradigm may be extended to such payments. So now please concentrate. It's not conceptually difficult, but okay, there are formulae. So Elisa, do they get the presentation?
The slides?
Yes.
This set of slides?
Yeah.
I think I don't know really if
Okay, so but you may watch my talk once again, so okay. And with some stops, so look at the formula. So but, yeah.
Okay.
Okay, so since M of T, remind you the definition of M here. It is a positive martingale, so the modification of M with respect to a series of payment defined so this is a weighted average of M's here. Stop me if you don't follow. Also is. Yes? So then we use eta formula. So just differentiate. And dm equals, of course, that. So this weighted average here. And if we collapse these two complex terms, we get MT times weighted average of volatilities. So that's a little d should be there, but I guess you know that. So we get Ito differential for the M of S, so M associated to sequence of payments. And of course, we proceed with the forward measure paradigm. So we construct a new winner process, adding the weighted average of volatilities. And that process is a winner process under the new measure, which is defined that way. And finally, we get that a price of a contingent claim, which is discounted not once, but several times, is this price under the forward measure, not discounted, but multiplied by something what looks like a deterministic short rate. I think that were the lengthiest formulae that you had. That is not deep, but you have to look at that very carefully. And I think that's the good time to ask several questions. Tomorrow you will hear about first Heath-Jarrow-Morton model, blah, 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 short rate models, BGM model, I think swaption pricing, Chayet model will be after tomorrow, I guess. So thank you for your attention, and we've got 5 minutes more to ask some questions.